In this video, we're going to discuss how some of those key features of the polynomials in the previous video result in certain behaviors in the graph. The first behavior that I want to talk about is the end behavior. So let's say we look at a polynomial and determine that the degree of the polynomial is even and the leading coefficient is positive. Then what will happen is the result will be that the ends of the polynomial, as x goes out right as far as possible and left as far as possible, they will have two ends facing up. Let's assume that the degree is still even, but now if you don't mind, I'm going to abbreviate. Leading coefficient is LC. The leading coefficient is negative. Then what will happen is those ends will turn from facing upwards to facing downwards. Let's assume now, instead of even, that the degree of a polynomial is odd. And the leading coefficient is positive. Then what will happen is the left end will be going downwards to negative infinity, and the right end will be going upwards to positive infinity. If the degree stays odd, but the leading coefficient is negative, those ends will change directions, and the left end will be going up to positive infinity, and the right end will be going to negative infinity. The next key features that I wanted to talk about are the zeros of the polynomial and how we can identify those. Let's say, for instance, I had a graph that had a shape kind of like this. The zeros are places where the function has a value of 0. So we'd actually have two of those, here and here. And let's just say, for instance, that this value right here was x equals -2. And let's say, for instance, that this value here was x equals +1. Those give me a good idea as to what the factors of this polynomial will be. I know that this polynomial is somehow going to take the form f of x equals x plus 2 and x minus 1. But we're going to talk about one distinct or interesting characteristic here. How would I know those? First of all, are x plus 2 and x minus 1 would be the factors. Well, I know that because if I was to plug in x equals -2, let's say, I'd have -2 plus 2. One of those factors would result in a 0. Or if I plugged in 1, 1 minus 1 would also be 0. So what we notice is that in this form, these values of a would be zeros. The next thing that I notice is this point here has an odd behavior. That is actually showing multiplicity. That x plus 2 factor is going to be multiplicity 3. How do I know that? Well, I know there's an invisible, let's say 1 here. 3 plus 1 is 4, which means I have an even degree. And the next thing that I would note is the leading coefficient would have to be negative. I know that because I have two ends that are facing downwards And so therefore, I would have to have an even degree that's negative. All right, so let's try and put this into application now. The first thing as I look at this graph I notice is that the zeros occur at x equals negative 3 and x equals 2. Those values need to be substituted in for these R2s. R1 and R2, I should say. So f of x was going to equal x minus negative 3 and x minus 2 to some power of p. So far I know f of x equals x plus 3 and x minus 2. The last thing that I need to determine is what that power of p should be. Notice how this graph has two ends facing up. So I know I need an even degree. And this bend in the curve shows me that there's some sort of multiplicity other than 1 happening at that point. So I'm going to say f of x could be x plus 3 and x minus 2 with a p-value here of 3 to make an even multiplicity, since I know there's an invisible 1 here.